Okay, welcome everyone for this week's live session. So, in this week, we will discuss some problems related to the application of integral, specifically in calculating the volumes of the solid generated by revolving some region in xy plane about a fixed axis, and we will also calculating their areas of such solids which you have after you revolve a particular region about an axis. So we'll calculate your area and volume of such solids using integration, and also we'll see some problems where we have to calculate length of curves or smooth curves. Okay. Okay, so remember that last time we have seen a method using which we have calculated volumes of solids of revolutions, right? And that method we were using the so-called disk method or the slicing method, where we take slice of our solid which is generated after the revolution, and we take slice perpendicular to the axis of revolution. Okay, and we see what is the shape of the slice. So if the shape of the slice is very nice, that we actually know its area, so we can integrate the area of the slice across the whole interval, whatever the possible range of that particular variable is there. We will integrate it, and then we get the volume. Okay, and if in some particular case those slices are disk, okay, so if they are nice disk, then the method is called disk method, and for the disk we know the area of disk very well, right? It's pi times the radius square, and this method we call this the disk method. And similarly we had the one washer method which is actually based on the disk method. Okay, so in that case the slices are not actually disk, but they are circular regions where we call them annulus or washer, where in if you from the disk, it's like if you have two concentric circle, then the area bounded by those two concentric circles, that is called the annulus. Okay, and the area of that annulus we can easily calculate, because you can calculate the area of the bigger disk and then subtract the area of the smaller disk, and that's how we can calculate the area of volume of the surface of revolutions or solids of revolution. But today we will see a different method, and that we call a cylindrical cell method. Okay, so let's move to our first problem, and while solving this problem I'll explain what is the cylindrical cell method, right? Okay, so our first problem says that we have a region D in the first quadrant. Okay, so the region is the first quadrant, means it's already bounded by positive x and y axis. So let's draw this region. We try to draw this region. Okay, so this is positive x axis, and then we have positive y axis, and then there is a region. And the region is bounded by some lines and a curve. So what are those lines? So there's a line x equal to 3. So let's take this line to be x equal to 3, and there's a line which says that y equal to root 3. Let's call this root 3. So this is point 0 comma root 3, and this point is 3 comma 0, and then we have these lines. Okay. Okay, let me draw the region first. This is the line y equal to root 3. This is our line x equal to 3. This was the point 3 comma 0, and then there is a curve. Okay, so what is that curve? Is this is a parabola, right? It's x equal to 3 minus y square. So this parabola, you can see that in this equation, if you put y equal to 0, then you get x equal to 3. That means the vertex of the parabola is here, and then if you put root 3 and minus root 3, right? If we have this is minus root 3 also. So if you put y equal to root 3 or minus root 3, then x becomes 0. Right? That means you are on the y axis. So The parabola is like this. You have to join these points. Okay, so you understand. So this is the arc of that parabola, one piece. We can say the arc. Okay. And then so this part is in the first quadrant and bounded by the parabola, arc of the parabola, and the two lines, which one is y equal to root 3 and another is x equal to 3. So we have to revolve this particular region about x-axis. Okay, so it's given that we have to revolve this about x-axis, and then a solid will generate. Okay, you get one solid. Okay, so that solid will look like something like this. Let if I try to draw this solid. Okay, so it will be very symmetric. It is a circular solid. Yes, it will be something like this. Maybe the figure is misleading, so okay, let's not draw it. But you can see that the solid which you get, we want to find the volume of this solid. Okay, so one method which you can always use is the disk method, because you can take slices. Okay, so what will be slices? Again, you can see that in this case slices will be annulus, right? So this is our axis of revolution, x-axis, and then you can take slices by perpendicular planes, about the planes perpendicular to the axis of revolution, and then there is a this particular length will be the radius, right? So there will be inner radius and outer radius. If you revolve this particular piece of arc, it will give you a circular region in the solid, a cross section of your solid, which will be bounded by two concentric circles. Okay, so the center of circle will be this point. Okay, this is the center of circle, and this part is inner radius, and then you have this part to be outer radius. Okay, so part inner radius and outer radius. One way to find the volume, to use the disk method. So let's call it small r and capital R. Okay. So what will be the capital R? So capital R is the distance, right? This particular distance. How much is this? This is the exactly root 3. Okay. The outer radius is root 3. And then what is the inner radius? Small r. That is not very difficult to find, because you can see that for finding this inner radius, you have to subtract from the root 3 this particular distance, right? Okay, it is this distance. So the inner radius the is equal to y. Okay, at a distance. So if we are taking these planes at a distance x from the y-axis, then the length y is exactly equal to your inner radius, and then you can see that y is equal to. Okay, now you have to find the volume, right? So how do you find the volume? For that, you have to find this area and then integrate it over all possible range. So possible range means you have to see up to which range your x varies, right? Right? Your x varies in this case between 3 and 0. So the what will be the area of this annular region, or the Wasser, or the, okay? So the area will be pi times the outer radius square, which will be 3, and then inner radius square, which will be 3 minus x. Okay, and then you integrate between 0 to 3. This is one method to find the volume. Then you have pi times x dx from 0 to 3. So pi x square by 2. The integral of x will be x square by 2. Then you put upper and lower limits. So if you put upper limit, then you get 9 by 2, right? Because integral is x square by 2. So it's pi times 9 by 2. Okay, so this is the one of the method by which you can find the volume, but we want to find the volume using a different method. Okay, so because in this particular week the cylindrical cell method was discussed, so the problems will be solving these problems using the cylindrical cell method. So this was disk method. Okay. You can say disk method or washer method because our disks were hollow, they have holes inside, right? So these are sometimes called washer method. But now we will be using something called cylindrical cells method. Okay, so what are cylindrical cells? So cylindrical cells are they they are hollow cylinders. Like you have this annulus, and you can okay. So you have you can take a solid cylinder, and then if you remove a part of the cylinder, okay, from inside, a small part, like we have removed a small disc from the disc, that circular disc, and we got annulus washer. Similarly here you get a cell if you remove this smaller cylinder from the inside. So this kind of thing is called a cell or a cylindrical cell. Okay, so now how, so now what is our idea? Our idea is that we will divide our solid as a union of very thin cylindrical cells, and we add all volumes of all these cylindrical cells, right? Like in this particular case, in our given example, we had this parabola, okay, and then okay, so this was our parabola, and then these were two lines, and we are revolving about x-axis, right? About this axis, we are revolving this particular region. So now what we can do, we can divide our y-axis, the perpendicular axis about which the axis which is perpendicular to the axis of revolution, that we can divide into some we can that interval divide into partitions. Okay, and for each partition you can take this piece, this rectangular looking like piece, but it is not exactly rectangular, it looks like this. Okay, so at one side this is and on this side it is curved, little bit curved, like this. Now, if you revolve this particular strip about your x-axis, then you can see that you will be able to generate a cylindrical cell. This will generate a cylindrical cell, right? So the okay, so the idea is to find the volume of this particular cylindrical cell, because there will be a lot of cylindrical cell. For each partition, there is a cylindrical cell, right? This particular piece also gives a cylindrical cell. Then there is a, so all these pieces. So as many partition point you have, there are as many as cylindrical cells, and then you have to add volume of each cylindrical cell, and then you integrate. Okay, so for that we have to find the volume of a cylindrical cell. So what is volume of, okay, so what is this volume? So you can see that the volume of a solid cylinder, that we all know, it's given by pi r square times h, right? So the pi r square just gives the area of the cross section, and then you have to multiply it by the height, and then you get the volume, okay, of the cell. But here our cell is hollow, so there is a hole in between. Okay, so what can we do? We to find the volume of the cylindrical cell, we can cut this cell by this arc. So assume that along this arc we are cutting our cell. Then you can imagine that your cell will open like this, right? and it will be small. There will be a small thickness. It will look like a cuboid. Okay, to find the volume of the cell, you have to multiply this length, all these lengths, right? You need to know all these lengths, the length, height, and breadth. Okay, so we assume that our each cell has some thickness. Let's call this thickness to be dx or dy. Okay, so in this case, our thickness, this small length, we call them dy. It will be dy, uh, thickness. And then this particular, okay, so this is the height of our cell, and there is a radius of our cell. Okay, so what is the radius? So radius of the cell is this length, the average of this length, because this is our axis of radiation, axis of revolution, and about which we are rotating the cell. So this is the radius of our cell. Okay, and this is our height of our cell. Okay, and this particular part, this length, you can say it is the thickness. Okay, so how do we find the volume of the cell? This length is 2 pi r, which is the radius. So 2 pi times the radius, right? It's like the perimeter of the circle. Okay, the perimeter of this base we are finding. And then we have this height of the cell. And then we have this dy. So like this, you can find 2 pi times, we can write as cell radius into cell height, and then into thickness. Okay, and this everything we integrate, so that our y varies in this partition. Let's say from 0 to some particular number a, or let's say a to b. If this was not 0, you are finding it from particular specific point, then a to b. You integrate this from a to b, and you get your volume of the solid. Okay, okay, so let me write, this is just the volume of your cell. Okay, so this is the volume of cell. And now what is the volume of the solid? Volume of the solid, you integrate everything, right? 2 pi, let's call radius r, h is the height, and dy. Okay, so this is the cell radius and this is cell height. Okay, so in our example, let's see what is the cell radius and cell height, and then we will find its volume. Okay, so our example is, we are rotating this particular region, right? Okay, so this is x equal to 3, this is y equal to root 3, and we are revolving this particular part about x-axis. Okay, and this is y-axis. So our range of y is between 0 to root 3. Okay, now for this particular arc or a region, small region, what will be the cell radius? Let's say we are at a distance of x. Okay, this is at a distance x, and then this will be at a height y. Okay, so what is cell radius? This is y, and what will be cell height? Okay, so this is the height, it is x. Okay, and thickness, we will take dy. Okay, because we have to integrate this on the x-axis. So what is the volume of, okay, so volume of solid is equal to integration 2 pi times radius into height into dy, where y is varying from 0 to root 3, right? So let's write everything. So what is radius? Radius is simply y. What is height? Okay, Okay, so cell height is not x. Okay, okay, so this is we are at a distance x, but cell height is this. This length is cell height. Okay, at a distance x. So cell height is not x. So what is cell height? Everything minus x. Okay, so this length, from this length we subtract x. So cell height is 3 minus x. Okay, so 2 pi y and 3 minus x. But what is x? Because we know that our parabola has this equation. So what was the equation of parabola? It is x equal to 3 minus y square. Okay, this is 3 minus x, which is 3 minus y square, and then dy. So our integral finally becomes 2 pi y cube dy. Okay, so this is our integral. Now it's not very difficult to find the volume. Okay, so volume of solid is equal to integral from 0 to root 3 of 2 pi y cube dy, which is equal to, you take to integrate y cube, you have y to power 4 by 4, and then you have to put upper limit and lower limit. Okay, so you have 2 pi times, okay, so what is root 3 to power 4? It will be 9, and then divide by 4. So you have 9 pi by 2, right? You can verify that from the disk method also we get, or Wasser method also we get the same volume, right? From Wasser method, here in the first slide I have used Wasser method, and the volume turns out to be 9 pi divided by 2. And similarly, if we use a different method than cylindrical cell, then the volume turns out to be same. So it doesn't matter if you use the Wasser method or cylindrical cell method. Okay, the volume will become same. Okay, so are there any questions till now? Okay, so I'll just wait for 2 minutes, and then we will start our next problem. Till now, you can ask any of your doubts if you have. Okay, so let's start with our next problem. Okay, so again, in this second problem, we have to again find the volume of a region, of volume of a solid of revolution. Okay, so let's see which region we are revolving. So this time we are revolving about this region D about yx. Okay, so let's draw this region here. We are revolving about y-axis, and then this region is bounded by two lines, x equal to 3 and y is 0. Okay, so what is y 0? Y equal to 0 is, this is x-axis, and the region is in the first quadrant, and then there is a line x equal to 3. Let's say this is line x equal to 3, and there is a curve which is given by 9x divided by x cube plus 9. Okay, now you can see that denominator is well defined here. Why? Even though denominator can become 0, so when can it become 0? Precisely minus 9 to the power, okay, 1 by 3. Okay, so for x equal to minus 9 to the power 1 by 3, denominator becomes 0. But since we are in the first quadrant, therefore x will always be positive. Okay, so therefore x cannot become this quantity, and that's why the denominator is well defined. So there is some curve. Okay, so let's say where this curve intersects x-axis and y-axis, when so you can see that if I put x equal to 0, then y becomes 0. Okay, so definitely this curve passes through origin 0 comma 0, and if I put x equal to 3, then what is y? Okay, so 3 cube is 27. Okay, so this is square root 36. So it's 27 divided by 6, which is equal to 9 by 2. Okay, so which is equal to 4.5. Okay, so when x is 3, this this is some curve which intersects x equal to 3 line at y equal to 9 by 2. Okay, so this is 3 comma 9 by 2. This point is 9 by 2, 0. Okay, so our curve lies in between. Right, let's say, so we don't know what is how this curve looks exactly, but that doesn't matter. Still, we can find the volume. Let's say it looks like this. Okay, so what is this region here? This particular region, we have to find the volume of this region. Okay, so again, and also we are revolving this region about y-axis. Okay. So you can use Wasser method also, because you can see that if you take slices out the plane perpendicular to y-axis, right, then you have Wassers or annulus. Okay, and you can find the area of the annulus and integrate it along the y-axis between 0 to 9 by 2. Okay, so what is the range of y here? Y varies between 0 and 9 by 2. And what is the range of x here? X varies between 0 and 3. Okay, so whichever axis you want to choose for doing the integration. So these are the ranges. We will use the cell method, cylindrical cell. Okay, so for that, since we are rotating the region about y-axis, cells, for the cylindrical cell method, we have to partition our x-axis, right? So that after rotation we have our cell. So this kind of a strip. Okay, so if you choose this strip of length, of thickness, let's say dx, and then you rotate it about the y-axis, then you get a cell. Okay, and for this cell, this length x is the radius of the cell. Okay, so let me explain again here. Okay, so at a distance of x, we are taking a small, very small strip of, let's say, thickness dx. Okay, so the thickness is dx, and because this is the axis of revolution, y-axis, so this x is the radius, and let's say this length y is the cell height. So what is cell radius? This is equal to x, and cell height is equal to y, which we have to write in terms of x because we are integrating in with respect to x, right? So y is equal to 9x divided by x cube plus 9. Okay, and hence, what is the volume? So volume of solid using cylindrical cells is equal to, let's say, what is this equal to? You have to find the volume of small cells, and that volume is 2 pi times radius, which is here x, then multiply by height, which is 9 times x divided by x cube plus 9, and then take a square root, and then thickness is dx, and then integrate. So the integrate means you add volume of all cylindrical cells. Okay, so you'll have a lot of cylindrical cell, and then you are adding the volume, and the volume we are adding where x varies between 0 to 3, right? This is the volume. Okay, so let's find the volume by doing this integration. So all these are applications of integration. Okay, so let's write volume, our required volume to be equal to v, and then this v is equal to integral from 0 to 3, 18 pi x square divided by 9 plus x cube under root dx. Okay, so how do we integrate this? We can see that in the denominator we have this x cube, and whose derivative is 3x square, and that in the numerator we have x square. Okay, so we'll substitute by the substitution method. Take 9 plus x cube equal to t, a new variable. Then if you differentiate both sides, then you get 3x square dx, that is differential. This becomes dt. And now since x varies between 3 and 0, this implies that 9 plus x cube, so what will be the limit? This is limit from 36 and 9, right? That is 9 plus x cube is t, that means t varies between 36 and 9. Okay, okay, so in the first problem I didn't noted that the second option is correct, right? Because the volume was 9 pi by 2. Okay, not okay. This first option is 9 pi by 2, not second option. Second option is 9 pi divided by root 2. First option is correct because this is 9 pi by 2. Okay, but we are doing the second problem. Let's come back to the second problem. Okay, so now our integral with respect to this new variable, this becomes v is equal to, okay, so 6 pi times 3x square dx, that will become dt, and then denominator we will have a square root of t, and that t varies from 9 to 36. Okay, now we all know what is the integration of square root of t. This is t to the power 3 by 2, and then you have to multiply by 2 by 3, right? And from limit 9 to 36. Okay, so what is this? 2 by 3 you can take outside, so you have 4 pi, and in the bracket 36 to the power 3 by 2 minus 9 to the power 3 by 2. Okay. So So that means 4 pi times. So what is square root of 36 is 6. Then you have to take the cube of 6. What is the cube of 6? It is 36 times 6. It is 216. Then you have to take 9 to the power 3 by 2. That means 3 cube, which is 27. Okay, so here there's a mistake. The integral of root t is t to the power half, not t to the power 3 by 2. So t to the power half into 2, right? Because the integral of t to the power n dt, the indefinite integral, is equal to t to the power n plus 1 divided by n plus 1 plus a constant, right? So here we had t to the power minus half. We are integrating t to the power minus half. So you have t to the power minus half plus 1, which is half, and then you have to divide by minus half plus 1, which is half. Then in the numerator, it will become 2. So this is equal to 12 pi. In the bracket, you have the square root of 36 and then square root of 9, which is equal to 12 pi times 6 minus 3. So this is equal to 36 pi. Okay. So the third option is correct here, 36 pi. Okay, so if you have any questions, then you can ask. I'll pause for 1 minute. Just wait for you for your question. Okay, let's now move on to the next problem. Okay, for next problem also we have to find the volume of a solid, which is a solid of revolution. But here now we are revolving the region about a line which is y equal to minus 5 by 8. Okay, so not now we are not revolving about x or y axis, so it's a different line, and then there is a region. Okay, so this region D is in the upper half plane. Okay, so upper half plane means this part, okay, above the x-axis, where y is positive, y and x-axis, and this region is bounded by two curves. So the equation of these two curves are given. So let's see where these curves intersects. Right, we should know where these curves intersect. So for that we have to solve these equation and find out where these two intersects before drawing the region. Okay, and the line about which we are rotating is this. Okay, let's assume that this is the line y is equal to minus 5 by 8. Okay, and again since we are revolving about this line, so our cylindrical cells, whatever the region we get in this upper half plane, for that cylindrical cell we have to partition our interval y. Okay, uh, which is along the y-axis. Okay, first let's find out what are those intersection point and what is the range of x and y. So we have two equation. 2x is equal to y square and 4x is equal to y to the power 4 minus 2y square. Okay, from this first equation, y square is 2x. Okay, then this equation implies that 2x whole square minus twice of 2x is equal to 4x. Okay, so this is our equation, because uh, instead of y square we put 2x in this second equation. Okay, if you solve this, then you have 4x square minus 4x is equal to 4x. That means you have 4x square minus 8x becomes 0. That means you can take 4x common, and then in the bracket you left with x minus 2. Okay? So this product 0 implies that either x is 0 or x is 2. Okay, so let's say if x becomes 0, then what is y? Y also becomes 0 because we have this first equation. And if x becomes 2, then what is y? Then y is just square root of 2x, which is twice 2 times 2. Okay. So these two equations intersect at point 0 comma 0 and 2 comma 2. Okay. So these are our intersection points. So this is our point 0 comma 0, and then we have a point 2 comma 2. So our curves, so there are two curves. Let's say this is our first curve, and then there is a second curve, and they intersect at these 2 points, and this is our region in the upper half plane. And this region we are revolving about line y equal to minus 5 by 8. Again, you can use cylindrical cell. You can use Wasser method to find out the volume, but we'll find the volume using cylindrical cells. Okay, so if you take a cell, that means you take the small strip. So you are partitioning this length. You have to just because you can see that our y now varies between 0 and 2, right? Because these two curves intersect at origin and 2 comma 2, and x also lies between 2 and 2. So but we are integrating along the y-axis. So we partition these y-axis and then this is a small strip, very thin, the very less thickness, and this we are revolving about this line y equal to minus 5 by 8. So what will be the radius? Let's say if we are at a distance y, okay, so this is, let's say, call it a distance y. So what will be the radius of cell? The radius of the cell is the distance from the axis of revolution. Okay, so this is the radius. Okay, this length is our radius, and what is the height of the cell? Height of the cell is this. Okay, this line, this distance. Okay, this is your height of, okay, height of the cell. Now to find this height, you have to see. Okay, so this point lies on one curve, and for that you have to find what is this point x comma y, and again this point also lies another curve, and you have to find at a distance y what is the value of x at this point, and then if you subtract, then you get the uh, height. Okay, okay, so now let's find out the volume. Now we have cell radius and cell height. Okay, so let me draw the figure once again. So this is 2 comma 2, and then we have this line y equal to minus 5 by 8, about which we are revolving this region. And we noted that if we take a small cell, then this will be the radius and this will be the height. Okay, so what is cell radius? So it depends where we are. Let's say we are at a distance of y. So the cell radius is equal to y plus 5 by 8, right? So this distance is 5 by 8, and this distance is y. So this is our cell radius. So what is cell height? Okay, so to find the cell height, you have to find what is this actual distance and what is this distance, these two, and then subtract. Okay, so let's call them, because these are coming from two different curve, we can call it this one x1 and this one we call it x2. We can write it the modulus of x2 minus x1. Okay, so we have to see which one is large, so that we take always the positive length, because height is a length, so we have to see. Okay, now because of the two equations, what are our two equations? Let's recall that from the one equation we get that x1 is equal to y square by 2, and from the second equation we get x2 equal to y to power 4 minus 2y square divided by 4. Okay, so what will be the height then? It is the modulus of this difference. Okay, so y square by 2, and then, okay, so first we are taking x2, so it is y square divided by 4 minus, okay, so this is y to power 4, and then we have minus y square by 2, and then we are again subtracting y square by 2. So this is equal to y to power 4 by 4 minus y square, and then what is will be volume? So we have to integrate along the y-axis, right? And the whole length is 2. So y varies between 0 to 2, and 2 pi times the cell radius. So what is the cell radius? It's y plus 5 by 8, and what is the cell height? is modulus of y to the power 4 by 4 minus y square dy. Okay. Now we have to see between 0 to 2 which is bigger. If y square is bigger than y to the power 4 by 4, or it's the different case. Okay. Okay, let's compare these two. So y varies between 2 and 0. So what are ranges of y square? Y square ranges between 0 and 4. And what are range of y to power 4 divided by 4? Okay, so y to power 4 divided by 4. So if you take to the power 4, so it will be 16, and divided by 4 is also 4. Okay, so both of these quantities vary between 0 and 4. Okay, but if y is strictly less than 1, then higher powers are smaller, right? Then y to power will be less than y square. Okay, so it's like if y is equal to half, then y to power 4 is equal to 2 to the 1 by 16, and y square is just 1 by 4. So 1 by 16 is actually strictly less than 1 by 4. But if y is greater than 1, then what will happen? Then larger power must be bigger than. Okay, so yes. So it's like if we take y to be 3 by 2. Okay, so what is y to power 4? Is 81 by 4, and what is y square? Is just 9 by 4. So you can clearly see that 81 by 4 is bigger than 9 by 4. So let's check what is happening at y equal to 1. Okay. So one curve we have 2x equal to y square, and another curve we have 4x equal to y to the power 4 minus 2y square. So if you put y equal to 1, okay, so y equal to 1 implies that x must be equal to half. And here if you put y equal to 1, then this will imply that x equal to 1 by 4th of. Okay, now you can see which one is bigger. Now it's very clear. Okay, so we are taking modulus of y to power 4 by 4 minus y square, right? So this is actually y square minus y to power 4 by 4. So y to power 4 by 4 is actually less than y square. Okay, so let's find out the volume now. The volume is equal to the integral from 0 to 2 pi times the radius. What was the radius? We know already. It's y plus 5, y plus 5 by 8, and then the height is equal to y square minus y to power 4 divided by 4, and then divide. Okay, so if we do this integral, then we get our volume. So let's find out this integral. 2 pi integral from 0 to 2. So what do? We expand this whole product and then we will integrate. Okay. So the first term here y cube, then we have y to power 5 by 4, then we have plus 5 by 8 y square, and we have 5 by 32 times y to power 4. Okay. Okay. So what is the integral of this whole quantity? So if you integrate y cube, then you have y to power 4 by 4. Integrate y to 5, you have y to power 6 by 6, then you have 24. And plus 5 by 8 times y cube by 3 minus 5 by 32 into y cube by 5 by 5, right? And this you have to take limits from 0 to 2. So if you put 0, then you get 0. So only upper limit matter here. So if you put 2, then this will give you 4. And from the second one, you'll have 2 to the power 6. So what is 2 to the power 6? Okay, so in the denominator is 24. To 24 is just 8 times 3, right? So 8 times 3, you have 2 cube times 3. So you can cancel 3 powers. Okay, and then you will have just 8 by 3. Similarly, these two also cancel, right? When you put y equal to 2, then this is just 2 cube and 8 is equal to 2 cube, right? So these two cancel. So you have just 5 by 3. And this 5 and 5 will cancel out. And then y to the power, and then you can see that this, if you put 2, then y to the power 5 is equal to 32, right? And therefore this everything will give you 1. So minus 1. This is your volume. So let's simplify this by 4 minus 1 is 3, and then if you add all these things, so minus 8 by 3 plus 5 by 3, this will just give you minus 1. So you have 4 pi. Okay, so the correct answer is 4 pi. The first option is correct here. Okay, so any questions? Wait for 1 minute, then I'll start with the next problem. Okay, so let's start with the next problem. Okay, so say the fourth problem also about the finding volume of solids of revolution. So let's see what is the region. So the region is given by two lines. So it's bounded by two lines. Let's draw it. Okay, so you can see that we have x equal to 0. So x equal to 0 means the y-axis, right? So x-axis and this y-axis is just x equal to 0. And then we have this line y equal to x. Okay, so let's see where these two lines intersect first. So y equal to x is this extended line. We all know this is very familiar to us. Okay, so y equal to x. And then we have this 2y equal to x plus 4. So let's draw this line. So we'll just find out 2 points. So if x becomes 0, so on the y-axis we have 2. There is a point on the y-axis. This point is just 0 comma 2. And if y becomes 0, then you have x to be minus 4. If x is 0, then y is equal to 4y2, which is 2. If y is 0, then x equal to minus 4. Okay, let's see where these two lines intersect, if they intersect at all. So we put second equation into the first equation. So the intersection points are 2y is equal to y plus 4. Implies that y must be 4 and x is also 4. So 4 comma 4 satisfies this equation. Okay, yes, 4 comma 4 is actually satisfying this equation. So where is 4 comma 4? Okay, let's again draw this line. Picture. So there are two lines. So one is y equal to x, another is 2y equal to x plus 4, which is precisely y equal to x by 2 plus 2. So it has slope half. So these lines are very close. It's like if this is my minus 4 comma 0, then this line is like this. Okay. So here you can assume that this is 0 comma 2. So that's why I was having this problem drawing this line. And this point is 4 comma 4. Okay. So this is 0 comma 4 and this is 0 comma 2. This point is 4 comma 0. Okay, so this is our region now. Okay, so this region we are rotating it about line x equal to 4. Okay, so what is the line x equal to 4? So this is our line x equal to 4. This is the revolution about which we are revolving. This is y equal to x by 2 plus 2. This is okay. So there are two lines basically, and this region we are revolving about line x equal to 4. Okay, and we have to find the volume of the solid generated by this revolution. Okay, so we will take cells. We'll use cylindrical cells. So let's take one cell. This this strip. We'll consider this strip, right? And if you revolve it, then you get a cell, right? Like this. This revolution will give you a cell. Um, so this is a very bad drawing. So basically, there is a cell. So what is the height of the cell? Okay, so at a distance x, so we are, let's call this x. So at a distance x, so we have to find the radius and height of the cell. So this is our axis of revolution. Let the line x equal to 4. That means this is the radius of the cell, right? So the radius is just the distance from the axis of the revolution. And what will be the height of our cell? So the height of the cell in this particular case is this length. Okay? This length precisely. So let's write radius of cell to be equal to, so the whole length is 4, so radius is 4 minus x. What is the height? Okay, so for finding height, we just calculate these two lengths. So this length, let's call it y2, and this length, call it y1. So y1 is on the axis, on the line y equal to x, and y2 length we are getting from the line y equal to x by 2 plus 2. Okay, so height will be y2 minus y1, and y2 obviously is bigger than y1. So what is y2? It is x by 2 plus 2 and minus x. Okay, so the height is 2 minus x by 2. So what is the volume? This is integral. So you can see that our x varies between 0 and 4. So the integral from 0 to 4, 2 pi times the radius. Radius is 4 minus x, and then 2 minus x by 2 dx. Okay, so the let's find out this integral and then we get our volume. So for finding the integral, we just expand this product. After expansion, you have 8 and minus 4 times x by 2, which is 2x. And then we have again a 2x, so 4x, and plus x square by 2 dx. Okay, let's integrate this. So the integration of 8 is just 8x, and then we have 4 times x square by 2, which is 2x square, and then we have x cubed by 6, and the integral is from 0 to 4. So from 2 pi, 8 times 4 minus 32 and plus 4 cube by 6. This is just 2 pi times 4 cube by 6. So pi 4 cube by 3. So what is 4 cube? 64 pi by 3. Okay, so the second option is correct here, 64 pi by 3. So any questions? No questions, so let's move on to the next problem. So this is our fifth problem, and in this fifth problem, we have to find the length of the curve. Okay, so this time we have to find the length of the curve. So this is a new problem. Again, an application of an integral. So how do we find the length of the curve? So let's say I'll just briefly explain this. So Let's say we have this curve between A and B. Okay, so we partition our interval into small parts, and from each partition we will calculate. So you can see that for each point we take these partition point, and then we take these chords and we add lengths of this chord. Okay, so these are all partition point. So in the limiting case, when you take the norm of your partition to goes to 0, so if the lengths of these small intervals this goes to 0, it's become very small. These chords are basically approximated by the tangents, right? So if this length is dx and this length is dy, so what is the length of our chord? It is dx square plus dy square under root. Okay, this thing we call ds. That means we have to integrate ds with respect to. Okay, so this ds, we are taking this as a function of t. Okay, so there is a parameter. So x is a function of t and y is also a function of t. So we are taking t as a parameter, so that if t varies between some interval between a and b, then your x varies between. So here we assume that this is our t axis. Okay, and in the 3 space xy space, this is the curve. Then you have to integrate the arc length. So this is called arc length. Okay, so we'll understand this problem with the solution with this example. So how do we find arc length? So this ds is just dx plus dy, dx square plus dy square under root. Okay, so because x and y are both functions of x, this is just dx by dt whole square plus dy by dt whole square, and you have dt outside. Okay, that means you have to integrate for values of t ranging from a to b, dx by dt whole square plus dy by dt whole square and under root. Okay, so this integral will give you your length of curve. Okay, now in the given problem, you can see that x and y are given as a parameter of t, where t varies between 0 and 3. Okay, so what is x? It's one third of 2t plus 3 to the power 3 by 2. And then what is y? It is half of 2t plus t square. Okay. So let's find out their derivative with respect to t, because we need that. So what is dx by dt? It's 1 by 3 into 3 by 2. Okay, so we apply chain rule. So you have 2t plus 3 to the power half into 2. And what is dy by dt? Is half of 2t plus 2. Okay, so if you simplify, then you can see that okay, so this is just equal to t plus 1, and if you simplify what is dx by dt, so you can see that this 3 and 2 will just cancel out, right? After this cancellation you will have left with 2t plus 3 to the power half. Okay, so let's find out the square, the arc length. So dx by dt whole square plus dy by dt whole square. Okay, so we have to find this square root. So if you take the square, then on one side you have 2t plus 3 and other side dy by dt whole square will give you t plus 1 whole square. Okay, so that means 2t plus 3 plus t square plus 1 plus 2t. This is just 2t square plus 4t plus 4. Okay, now it can be easily seen that this can be written as t plus 2 whole square, and we know that t varies between 3 and 0. Okay, that means t plus 2 varies between 5 and 2. That means t plus 2 is positive, right? So if you find ds, so the ds will be dx by dt whole square plus dy by dt whole square to the power half, right? Under root. This is precisely, and there is a dt outside. So we'll get 2t plus 2 dt. Okay, and hence the length of the curve, which is integral of ds, where t varying from 0 to 3 is just equal to 0 to 3 of t plus 2 dt. Okay. So if you integrate, then you have t square by 2 plus 2t, and this you have to take limits from 0 to 3. So you have 3 square by 2, which is 9 by 2, and plus 6. So this is 21 by 2. So 21 by 2. So last option is correct here. Okay, so any questions? Okay, so let's move to the next problem. Okay, so in this problem also we have to find the length of a curve which is given by this parametric equation. So x is this and y is this, where t varies between 0 and 2 pi. Okay, so let's directly find out here dx by dt. So what is dx by dt? So root 2 is outside, you have 1 minus cos t. So and what is dy by dt? Again root 2 is outside, and when if you differentiate cos t you get minus sin t. So it's okay. So let's calculate. Okay, so in the shorthand we write x prime t, right, and y prime t. So let's calculate x prime t whole square plus y prime t whole square. This is equal to, so if you square the derivative of x, you get twice of 1 minus cos t whole square plus twice of sin square t, right? Then if you take 2 common, so you'll have 1 plus cos square t minus twice of cos t and plus sin square t. Now you can see that sin square t plus cos square t becomes 1. So 1 plus 1 is 2. So you can take 2 again common. So you have 4, and then you have 1 minus cos t. Okay. Now remember that we have to take the, for finding ds, we have to take the square root of this thing, and that's why. Okay, so that's why we'll write this as in terms of half angle formula, right? So this is 4. So what is 1 minus cos t? Okay, so for cos half angles, but we have cos 2 theta. So there are two formulas. One is this cos square theta by 2 minus 1, and another is 1 minus 2 sin square theta by 2, right? Okay, so if you follow this, then 1 minus cos t just becomes twice of sin square t by 2. Okay, and hence what is ds? So in this case, dx is just square root of 8 sin square t by 2 dt, which is just twice of root 2 sin t by 2 dt. Okay, and t lies between 0 and 2 pi. So what is the length of our curve? Okay, so for finding length, take integral from 0 to 2 pi. Okay, so here we have to also note that when you take square root, we have to apply the modulus sign. Okay, like in the previous problem also, we did the same. When we take square root, then initially we have to apply the this modulus sign, but because we noted that t plus 2 is always positive, it lies between 2 and 5, and that's why you can open the modulus sign. Okay, so t plus 2 is positive. So same thing is here also, so sin t by 2. But since you can see that t lies between 0 and 2 pi, your t by 2 lies between pi and 0. And between this interval, sign is always positive, right? So 2 root 2. So you can open the modulus sin t by 2 dt. So 2 root 2 comes outside, and then you, what is the integral of sin t by 2? It's cos t by 2 and with a minus sign. So cos t by 2, and you have to multiply, divide by half. That means you have to multiply by 2, right? Twice, and take limits from 0 to 2 pi. So, okay, so minus 2 we also can take outside, but it's fine. So minus 2 times, so cos t by 2, that means we are taking cos of 2 pi by 2, which is cos of pi. So cos pi, and plus twice of cos of 0, right? So cos pi is minus 1, so it will be just become 2. Cos 0 is 1, so it is also becomes 2. 2 plus 2 is 4. 4 times 2 is 8, so this is 8 root 2. Yes. Okay, so the 8 root 2 is the correct answer. Last option is correct here. So this is not correct. Option D is correct. Okay, so let's move to the next problem. Okay, so in this problem, you have to find the area of the surface generated by revolving certain curve, okay, about axis. Now, this is a third application. You can say one more application of integration. Using the integration, you can also find the area of surfaces, which you get after you revolve a curve, right? So you can imagine that if you have this curve, let's say semicircle, and if you revolve the semicircle about x-axis, then what do you get for the revolution? It will give you some solid, right? Uh, it will give you the sphere, where the sphere is hollow, so only the surface is there, right? So we have to see how can we find the area of such surface of revolutions. Okay, so in general, if you have some curve, right, and you are revolving it about some axis, let's say you are revolving it about x-axis. Okay, so what can we do? We can again take partition of our interval, this interval, and we consider this small strip, right, between 2 point. Okay, so this part is not there, okay, inside part. So we are considering just a small portion of our curve, okay, this particular arc. So if you revolve this about x-axis, then this arc will give you a circular strip, right, like this. Okay, so if we are able to find the area of this particular strip, then if we integrate this along the whole range of interval along x-axis, then we get the area. But how do we get the area of this axis? Because you can see that this axis, so this strip is not okay. Okay, for this strip, this you have to find this length, basically the length of the arc, right, this arc element, because on the x-axis you have a small length, dx, and on the y-axis you have this length dy. So if you know the arc length of this small arc length, this is we call ds, then you can easily find its area, right? Because what is the area? This is like a cylindrical strip, okay, but not perfectly slender. So how do we find the area of a cylindrical strip? So if it is like this, okay, so you have to find the radius. So what is the radius? Whatever r, you find the perimeter 2 pi r, and then take the height, okay, h. This will give you the area of the cylindrical strip. But our strip, it is not cylindrical, okay. So for this thing, our strip is like this. It is little bit slant. It is a part of frustum, okay. If you have heard of this thing, it is like this. So because of that, here the height will be this much. Okay, so height is not equal to this arc length. Okay, so this length will be smaller than this length. Okay, so we have to find the arc length. So again, the idea is same. You have to find the radius and the area of this particular strip will be 2 pi r, but then you have to multiply it with the arc length ds. Let's call this arc length to be small ds, and then you integrate such small areas to get the area of your surface. Okay, so let's understand this with this given problem. Okay, so in this particular problem we have an arc of a curve. So it's a part of this curve between where y varies between 1 and 2, and we are revolving it about x-axis, and then we have to find the area. Okay, so if you are revolving about x-axis, then what will be the radius? Radius will be this length. Okay, so if at a distance x, let's say this was distance x, so at this particular distance x, so this height is the radius, because from the axis of revolution you have this much distance y, so this is your radius. Okay, so what will be the area of surface of revolution? This is equal to the integral 2 pi times the radius into arc length. Okay, and this you integrate. Okay, so now the integration, you have to see of which variable you are taking for integration, right? Because this arc length ds can be written both in terms of x or y. Okay, so we will write this in terms of x or y whenever whichever way it's easier. So this is your area. So how do we find the arc length? Okay, arc length ds is just equal to, you know that this is dx square dy square under root, right? So for us it's given that x is equal to, okay, so 8 times x is equal to 2y to the power 4 plus y to the power minus 2. Okay, so if you consider x to be a parameter, okay, so we can consider x a parameter. Okay, or okay, let's see this parameter in terms of t. Okay, so x as a function of t is equal to t, or let's say y as a function of t is equal to t, then x as a function of t is equal to 1 by 8 times, right? Because y is equal to t, so instead of y here we can write t. So we are parameterizing it, but our one of the parameter is this constant identity function. So y of t is t, just 2 times t to the power 4 plus t to the power minus 2. Okay, so this is the parameterization of this curve. Now you can find arc length. Okay, so what is dy by dt? It is 1, and then we have to find dx by dt. So it is 1 by 4 into 4 t to the power t cube plus minus 2 into t to the power minus 3, right? Hence t cube minus twice of t to the power minus 3. Okay. So what is the arc length? ds is equal to x prime t square y prime t square under root dt. Okay, okay, so let's not take a square root now, we will take it after. So first write what is square of ds. Okay, so y prime is just 1, so square is 1, so 1 plus t cube minus twice of t to power minus 3 square. Okay, let's expand it. 1 plus, so if you take the square, you get t to the power 6, then plus 4 times t to the power minus 6, and then minus 4 times, okay, so minus 4. Okay, so we missed this factor of 8 here, so you have to also divide here by 8. Okay, so when you divide by 8, you get a factor of 4 here, so divide by 4. Divide by 4. So now if you expand, this is 1 plus t to the power 6 and plus t to the power minus 6 divided by square of 4, which is 16, and then minus half, right? Which will be just equal to t to the power 6 plus t to the power minus 6 divided by 16 and plus half. Okay, now you can see that the ds square, okay, so we have dt also outside. The ds square, okay, so here also we have dt square. So ds square will becomes t to the power 6 plus t to the power minus 6 divided by 16 and plus half into dt square. But now you can see that this you can write it as a square of t cube plus t to the power minus 3 divided by 4 whole square, right? And hence the arc length ts turns out to be t cube plus t to the power minus 3 divided by 4 this time dt. Okay, and it's positive because t varies between, okay, so y varies between 1 and 2, but y we have assumed to be t, right? And hence t also varies between 1 and 2. Okay. Since y is equal to t, it varies between 1 and 2. Now can we find the area? So for that we have to find radius in terms of t, right? So what will be the radius? So radius will be y, and y is equal to t. So radius is t. Okay. What is the radius? So radius is distance from the axis of revolution, right? Distance from axis of revolution, which is here in terms of y, it's y, and y is equal to t, and hence area of surface is equal to the integral 2 pi times t, and then we have ds, which is t cube plus t to the power minus 3 times divided by 4 into dt, where t varies from 0 1 to 2. Okay, so if we find this integral, definite integral, then we get the area. So let's calculate this definite integral. So this integral is equal to, if you want, you can take 2 pi outside, integral from 1 to 2. Multiply t inside, you have t to the power 4 and plus t to the power minus 2 divided by 4, everything dt. Now you can easily integrate this 2 pi times. So first integral turns out to be t to the power 5 by 5. The second integral gives you t to the power minus 2 plus 1 divided by minus 2 plus 1, and the 4 we also have outside. And take integral from 1 to 2. The limits from 1 to 2. Okay. So if you put 2, then you have 2 to the power 5 divided by 5. So what is 2 to the power 5? Is 32. Okay. And in the denominator you have minus 1, right? Minus 2 plus 1 is minus 1. So in the denominator you have minus 4. That will become plus 1. That will become plus. So we have plus. Okay. So this is also let's write it t to the power minus 2 plus 1 is minus 1. Okay. So if you integrate t to the power minus 2, you have t inverse divided by minus 2 plus 1, which is minus 1, and that will make it no. So this will be minus and divided by 4. Okay, this we have to take limit from 1 to 2. So if you put 2, then you have to find inverse of 2, which is half. That means 1 by 8. Now you have to put 1. It will give you 1 by 5 and plus 1 by 2 pi times 31 by 5 minus 1 by 8 plus 1 by 8. Okay, so if you simplify it, in the denominator you will have 40. So what is 248 plus 5? It's 253 pi divided by 20. Okay, so second option is correct. 253 pi divided by 20. Okay, okay, so if there are any questions, let's let's wait for 1 minute. Okay, so let's start with the next problem. Okay, so we have to find the area of surface of revolution where we are revolving this curve where x varies between 0 and root 2 and y is non-negative, and we are revolving it about the y-axis. Okay, so let's find out what is y when you put x. Well, x lies between root 2 and 0. So if x is 0, so what is y? Because 9y square is 2 cube, so it is 8. This implies that y square must be 8 by 9, which will say that y must be square root of 8 by 9, which is 2 root 2 divided by 3, right? Because y is given to be bigger than equal to 0. When x is root 2, then what is y? So 9y square is equal to, so x is root 2, square is 2, so 2 plus 2 is 4. 4 cube, what is 4 cube? 64, right? So what is y square? It is 64 divided by 9, and this gives y to be the square root of this, which is 8 by 3. Okay, so these 2 points lies on our curve. So the curve is given by equation 9y square is equal to x square plus 2 whole cube. Okay, so let's draw a rough figure of this thing. So x, this is x-axis, and x value between 0 and root 2. So when x was 0, we get that y is 2 root 2 by 3. So some point here, x is 0, so y is 2 root 2 by 3. And when x was root 2, y was 8 by 3. Okay, so somewhere root 2 and 8 by 3. So assume that this is the point, root 2 comma 8 by 3, and between them there is a curve, so any curve. And this curve, we are revolving it about x-axis or y-axis. Let's see. Okay, we are revolving it about y-axis. Okay. So now you can see that if you revolve it about y-axis, that means your radius. Okay, so radius will be this distance, which is x. So at a distance of y, so let's assume that this is whole distance is y, and this whole distance is x. So what is the radius? Is equal to x. Okay, so let's parameterize this curve. Let's take x as a function of t to be equal to t. Then what is y as a function of t? This is t square plus 2 to the power 3 by 2 and divided by 9 to the power half, which is 3. Right? First from here, what is y? Is x square plus 3 whole cube divided by 9 and take power half. Okay, so now we have xt and yt. Let's find out the arc length. So what is ds? Or let's first find out x prime t. This is 1. What is y prime t? It is 1 by 3, and apply the chain rule. We have 3 by 2 outside, then t square plus 2 to the power half into twice of t, right? This is just t times t square plus 2 to the power half. So if you calculate x prime t whole square plus y prime t whole square, then you have 1 plus t square into t square plus 2. This is equal to t to the power 4 plus 2t square plus 1. Now this we can write as t square plus 1 whole square. Right? Okay. And hence, what is the arc length? ds, this is equal to the square root of x prime t whole square y prime t whole square dt, right? Which is precisely equal to t square plus 1 dt. So note that x varies between 0 and root 2, and x is equal to t. Therefore, t also varies between x varies between 0 and root 2, and this is equal to t. So t also varies between 0 and root 2. Now we can find our area of the surface of revolution. So the area will be equal to the integral 2 pi times the radius, which is x, but x is equal to t. Now the arc length is t square plus 1 dt, and t varies between 0 to 2. Okay. So if you find this integral, you get the area. So take 2 pi outside, integral from 0 to root 2. Expand the product. So it's t cube plus t dt 2 pi. So if you integrate, then you have t to the power 4 divided by 4 plus t square by 2, right? And take limits from 0 to root 2. So what are the limits? After taking the limits, you have 2 pi times. So root 2 to the power 4 will give you 1, and root t square will give you again 1. So 1 plus 1 is 2, so you have 4 pi as your area. Okay, so the third option is correct here. 4 pi is the area. Okay, so we will end our this live session at this point. We are already running out of time. So thanks everyone for joining. Okay, so next time I'll discuss the remaining problems related to the same material, where we will be finding surface areas and volumes of solids or revolution, and also some problems on the finding the arc length of curves. Okay, so thanks everyone for joining. Let's meet you next week.